Okay, so for number one, we are given this reaction here where we've got benzene, that's C6H6, reacting with bromine to produce bromobenzene and hydrobromic acid. So I'm just going to call these benzene and bromine and bromobenzene because that's easier to say for me than C6H6. But just so you know what I'm referring to. So in the problem, we were given a couple numbers. We were given that we have 34.6 grams of benzene and 68.4 grams of bromine. So the first step to determining what the theoretical yield of bromobenzene is going to be is to determine which of these we're going to run out of first. And that is called the limiting reactant or the limiting reagent. Those both mean the same thing. So let's go ahead first of all and determine which of these two is going to be our limiting reactant. I'm going to go ahead and start with benzene. So I've got 34.6 grams of benzene. And I need to convert this into moles. So I'm going to go to the periodic table and say for every 1 mole of benzene, I have, so there, a mole of benzene weighs 78.114 grams. So grams cancel, and now I have moles of benzene. And then if we go back and revisit our equation here, where we can determine what the mole-to-mole ratio is, we see that we have for every 1 mole of benzene that's consumed, 1 mole of bromobenzene is produced. So there's a 1-to-1 mole ratio here, and we can express that in our calculation like this. So 1 mole of C6H5Br, so that's bromobenzene, 1 mole of bromobenzene is made for every 1 mole of C6H6 that's produced. So now these moles cancel, and now my units are in moles of bromobenzene. And I'm done. So let's see, how much does this equal? I'm going to run this through my calculator, and it's 0.443 moles of bromobenzene. So basically what this calculation is saying is, supposing we had a finite quantity of benzene, so that's our 34.6 grams, and an unlimited supply of bromine. So we don't care about how much bromine it's going to take. We have an unlimited supply. How much bromobenzene are we going to make? And that turns out to be 0.443 moles. So now let's do the same thing for bromine and say, well, suppose now we have an unlimited supply of benzene and only 68.4 grams of bromine. How much bromobenzene are we going to make? So let's go ahead and do that. So we have 68.4 grams of bromine times for every 1 mole of bromine. There are going to be 2 times 79.904 grams. And remember, the 2 just has to be there because just like we had with the oxygen, we have a 2 right here. And then going to our mole-to-mole ratio, we got 1 mole being consumed here of bromine, and we're producing 1 mole of bromobenzene. So we just express this the same way as above. So now our grams cancel, moles cancel, and now once again we are in moles of bromobenzene. And then if I run this through my calculator, I get 0.428 moles of bromobenzene. So now the question is this. Using these two numbers, which reagent is it, or reactant, is it going to be the benzene or the bromine is going to be our limiting reactant? So it's going to be our bromine because we can only produce 0.428 moles of bromobenzene with the bromine. We ended up producing more bromobenzene if we just looked at the benzene here, so it turns out that the benzene we have in excess. What's going to run out first is going to be the bromine here because we produce less of the bromobenzene. with the bromine. So the bromine, therefore, let me move this up a little bit. So the bromine is therefore our limiting reagent. Or, I'm sorry, I keep going back and forth. I'm going to be specific and call this a reactant. Limiting reactant. So that's what the bromine is. So we've already done most of the work because we've determined that bromine is the limiting reactant, so that's going to be what we run out of first. And we've also determined how much of the bromobenzene we make. So we're almost there. The last thing we want to do, just to answer the question, is determine the number of grams of bromobenzene we make. So if we know that the most we can make before we run out of the limiting reactant is 0.428 moles of bromobenzene, then we can just go to the periodic table and look up the, or determine what the molecular mass is for bromobenzene. It turns out that you would get about 157.01 grams per mole. Now our moles cancel. And this would tell you here the number of grams of bromobenzene that you produce. So we have 67.2 grams of bromobenzene. So that is B. So the right answer for number 1 is B. Alright, so number 2 says maltose is a fermentable sugar which is converted to alcohol and CO2 in beer. So it's asking us to determine here, this is maltose, this is the chemical formula for maltose. It's asking us to determine what is the percent composition of maltose. So essentially what we're asking is, if we know what the molecular weight is, and I just went to the periodic table and calculated this, if we know how much a mole of this molecule weighs, then what we're asking by determining the percent composition is how much of that mass is carbon, how much of that mass is hydrogen, and how much of it is oxygen. So the way I like to go about doing this is I just look at this, this chemical formula, and I go, I know I have 12 moles of carbon, the element carbon, for every 1 mole of the molecule maltose. And if I want to convert it into grams so that I can compare grams to grams for a percent, then I just go to the periodic table and I find how many grams a mole of carbon weighs. And it turns out to be 12.011 grams. That's how much a mole of carbon weighs. So now my moles of carbon cancel, and with this equation what I'm saying here is that I got 12 times 12.011 grams of carbon in a mole of this molecule. So if I take this and run it through my calculator, which I can do right here, I would determine here that 12 times 12.011 would be 144.132 grams of carbon per mole of maltose. Well, where do we go from here if we want a percent of the molecular weight for a mole of maltose? Well, all I'm going to say is that percent is just going to be the grams of carbon per mole of maltose per total grams per mole of maltose. That's all I'm doing. I'm just seeing how much of the total mass is carbon. And of course I'm going to multiply that by 100 so I can slap a percent sign on there and I have my percent. So what I'm going to do is just plug and chug. So I've got here that I have 144.132 grams of carbon in a mole of this molecule, and a mole weighs 342.3 grams. So if I do that, I would find that I have 42.1% carbon in the molecule maltose. So I can do the same thing for hydrogen and for oxygen, and I would find that I have 42.1% for carbon, and I have 6.5% for hydrogen, and I have 51.4% for oxygen. So therefore, the right answer for number 2 is D. For number 3, we are given a molecule that is called Ritalin, and where number 3 asks, what is the percent composition of Ritalin? That is actually a mistake. What that should say is, what is the chemical formula of Ritalin? Or you could also say molecular formula. Either one works. Both are talking about the same thing. So what is the chemical formula of Ritalin if it has 72.07% carbon, 8.21% hydrogen, 6% nitrogen, and 13.72% oxygen? So there's lots of different ways to do a problem like this, but the way that works for me is to start out by saying, well, suppose I have 100 grams of Ritalin. And the reason this is nice is because now 72.07% of 100 grams is just 72.07 grams. And likewise for all the other percents. So what this essentially becomes is 72.07 grams of carbon are in 100 grams of Ritalin, 8.21 grams of hydrogen are in 100 grams of Ritalin, 6.00 grams of nitrogen are in 100 grams of Ritalin, and then finally 13.72 grams of oxygen are in 100 grams of Ritalin. So we just, by supposing we had a lump of 100 grams of Ritalin, 72.07% of that lump is going to be carbon. And since 72.07% of 100 grams is 72.07 grams, that's how we convert it into grams. And we did that for all of them. So that tends to work out pretty nicely. So when you're looking at a chemical formula for something, what you're really looking at is if you had a mole of that molecule, the subscript indicates the number of moles of that element that you have in the molecule. So, for example, like if we went back to the maltose example, then in maltose we had 12 moles of carbon in a mole of maltose. So what we want to do in this situation is we want to take advantage of the same idea, and we want to go from grams of all of these into moles. And the way we're going to do that is just visit the periodic table. So I'm going to show carbon here. First off, so I've got 72.07 grams of carbon, and a mole of carbon weighs 12.011 grams. So my grams are going to cancel, and here what I get is, turns out to be 6.00 moles of carbon. And I can do the same thing for hydrogen, where I've got 8.21 grams of hydrogen, and every mole here weighs 1.0079 grams. Grams cancel, and now we're in moles of hydrogen. And now give me a second here, and I'm going to go ahead and do this for the other two elements, and now we can go from there. Okay, so here's what I've put together. I've done carbon, hydrogen, nitrogen, and oxygen. So I've just taken these grams and have converted them into moles. That's all I've done. So now that I'm in moles, I have the basis for a chemical formula. So I'm going to move this up a little bit. And I'm just going to take these numbers and make them into a chemical formula. So I've got carbon, I've got 6 moles of carbon. And then hydrogen, I've got 8.15 moles of hydrogen. And then for nitrogen, I have 0.428 moles of nitrogen. And then the oxygen, I have 0.858 moles of oxygen. So I've just, essentially what I've done is I've taken all of these numbers and have made them into a chemical formula right here. So we're almost done. We have our chemical formula, but now we need to make it into integers. So an easy way to make everything into integers is to divide everything by the lowest number. So this is a big number, that's a big number, that looks like the smallest number. This one is larger, so the nitrogen had the smallest number. So I'm going to take everything and divide it by this number. So I've taken everything and divided it by 0.428. And I haven't really changed the chemical formula because I've divided everything by 0.428. But now what I've done is I have made the chemical formula in such a way, I'm really bad at multitasking here. So I've made it in such a way that now all of the numbers are very, very close to integers. And I can make them integers by rounding them. So I'll show you here in a second once I get all this written out. Nitrogen, of course, is 1 because we've divided its coefficient by itself. And oxygen is 2.005. Okay, so this number is really close to 14. This number is really close to 19. Nitrogen, I guess, by definition is 1. And then oxygen is really, really close to 2. So the chemical formula that we end up with is, if we just round all of these, is C14, H19, NO2. And the one that corresponds to is C. Number 4 gives us this equation where we have sodium carbonate and hydrochloric acid reacting together to make salt, CO2, and water. And what it's asking us to determine is how many liters of CO2 will be formed. And basically what that is asking is how many moles of CO2 are formed. Because once we determine the moles, then we can use the unit conversion to take us from moles of CO2 into liters. And we'll save that for the very end. So for now, let's just focus on determining how many moles of CO2 we make. And with that being said, this problem is really no different from any of the others we've done so far. So the first step to doing a problem like this is determining which of these two reactants is going to be the limiting reactant. And let's go ahead and just start with sodium carbonate and see if this one's our limiting reactant. Well, we won't know until we do both of them. But let's just go ahead and do this one. 3.25 grams of sodium carbonate. And, well, I'm going to shorten this a little bit in the interest of time, but basically what I'm going to do here is just make a little shortcut where here I would say for every 1 mole of sodium carbonate I have a certain number of grams, and I would just calculate that from the periodic table. Yeah, so I'm going to say this equals 0.0307 moles of sodium carbonate. And going back to the balanced chemical equation, we see that for every 1 mole of sodium carbonate that we consume, we produce 1 mole of CO2. So I'm going to take this 0.0307 moles of sodium carbonate, and I'm going to say for every 1 mole of CO2, there's 1 mole of sodium carbonate. So now my moles of sodium carbonate cancel, and I am in units of moles of CO2. Well, that's my kind of mental math. That just gives me 0.0307 moles of CO2. Quite easy. Now let's do HCl. So we have 3.10 grams of HCl, and again, if we go to the periodic table and we add up the molar mass of chlorine and hydrogen, we would find that, and then we did the calculation with that molar mass, we would find that we have 0.0850 moles of HCl. And so then that means that we have this many moles of HCl. And now we got to go back to the balanced equation and look at the mole-to-mole ratio. So we have 2 moles of HCl are consumed and 1 mole of CO2 is made. So we have to take that into account here and say that 0.0850 moles of HCl times, for every 1 mole of CO2, I need 2 moles of HCl. And that is going to equal 0.0425 moles of CO2. So now, using these two numbers, once again, which of these two is it going to be? Is it going to be sodium carbonate or hydrochloric acid is going to be our limiting reactant? And it's going to be the sodium carbonate. And we know that because we end up making less CO2 with that one. So when we put together the sodium carbonate and the hydrochloric acid, we're going to run out of the sodium carbonate first. That's the one we're going to run out of first. So we have plenty of HCl. It's the sodium carbonate that's going to limit the reaction. So sodium carbonate, let me come back up here. So sodium carbonate is the limiting reactant. Well, we now have the number of moles of CO2 that are made with the 3.25 grams of sodium carbonate. So we can just go ahead and use that, 0.0307, to do the final step in the problem. So we have now moles of CO2, and the final step in the problem requires us to calculate the number of liters that many moles of CO2 occupies. So we know from the problem, it's given to us as a unit conversion that 1 mole of CO2 is going to occupy a volume of 22.4 liters. So if we have 0.0307 moles, then we can figure out how many liters that is going to occupy. So our moles cancel, and we go into liters, and here, what that's going to give us is 0.69 liters of CO2. So the answer that corresponds to is C, 0.69 liters. So lastly, for number 5, we have this equation where we've got 0.23 moles of sulfur and 0.25 moles of oxygen, and they're going to react to make SO3. And what we're asked to determine is what is the percent yield of this reaction. And we're given that we have an actual yield, so we went into the lab and we did the experiment. We found that we obtained 12.46 grams of SO3. This is our actual mass. And so what we're supposed to do here is calculate how much we would theoretically get if the reaction went to 100% completion. We know that chemistry is not perfect. Some things happen, side reactions happen, and we lose some product when we purify it and whatnot. So our actual yield turns out to be a little bit less. But to figure out what the percent yield is, we have to figure out how much the theoretical yield is going to be. So in order to do that, we have to, as always, determine which of these reactants is going to be our limiting reactant. So I'm going to start off with sulfur, and I know I have 0.23 moles of sulfur. Going back to the balanced chemical equation, excuse me, we see that we have 2 moles of sulfur that are consumed and 2 moles of SO3 that are generated. So we can say we got 2 moles of SO3 for every 2 moles of sulfur. Alright, and that's really easy mental math. That's just 0.23 moles of SO3, and that's what we have. Now let's try the oxygen and see if that's our limiting reactant. Now we'll be able to make that distinction. 0.25 moles of oxygen times, or I guess I could be specific here, O2 times, we have our mole to mole ratio here from the equation, and we see that 3 moles of oxygen are consumed and 2 moles of SO3 are produced. So we have 2 moles of SO3 that are produced and 3 moles of oxygen are consumed. So our moles cancel, and that gives me 0.167 moles of SO3. Okay, so now we know how many moles we make with each of these reagents. So which of them is the limiting reactant? That would be the oxygen. So the oxygen right here is the limiting reagent. Or I'm going to be specific here, limiting reactant. Because it's one of the reactants here in the equation. So oxygen is our limiting reactant, which means that we're going to run out of the oxygen first. So when we run out of oxygen, we would have made, right here, 0.167 moles of SO3. So we're almost done here. 0.167 moles of SO3 is how much we make. And if we want to do the percent yield, and we've got grams, then we have to figure out some way to calculate grams from these moles. And the way we do that is we go to the periodic table and we calculate how much a mole weighs. And I went ahead and did that ahead of time. So that's 80.062 grams of SO3 is how much a mole weighs. So moles cancel, and now we're in grams of SO3. So this is now going to be 13.37 grams of SO3. This is our theoretical yield. That's our theoretical yield. So going back to the equation for percent yield, this is going to be now our actual yield, how much we got when we did the experiment, divided by the mass of the theoretical yield. And that's 13.37 grams. So we just do this, and we get 93.4%. And that is A. So the right answer for number 5 is A. And there we go. That was worksheet number 6.